Alrighty, so today we're going to talk about absolute and conditional convergence. This isn't necessarily a test, but this is something we can use all of our tests for. So we'll be reviewing everything we've talked about for this. And this applies when we have a series in which the terms are sometimes positive and sometimes negative. It doesn't necessarily mean alternating, but you could just have some positive, some negative, or maybe negative, all negative, something like that. And we have a theorem here that says if the absolute value of a series converges, then the non-absolute value also converges. And this will be a very important theorem, but I think it'll be a little bit easier to understand after we look at a couple of examples. So first, let's look at an example that is going to help us really understand what this absolute convergence might be about. And that's going to be the alternating harmonic series. Right, so we already know that the series n equals 1 to infinity of 1 over n. This is the harmonic series. And what we have here is just the alternating version of that because it has the -1 to the n plus 1. So this series, if we use the alternating series test on this, so 1, we do the limit as n approaches infinity of just a sub n, which is 1 over n, we get 0. And then 2, 1 over n, and 1 over n plus 1, the next term is going to be decreasing. So this converges by the alternating series test. However, we already know the harmonic series without the alternating is a p series with p equals 1, and so this diverges. We've talked about that many times. So this guy here is the absolute value of our series -1 to the n plus 1 over n. And the absolute value of our series, so the only positive part without the alternating part, it diverges. But the original series itself converges. And this is exactly what conditional convergence means. It means when you have only the positive part of the series, you get diverges, and when you have the alternating part, or the part that has some positive, some negative, we converge. So the alternating part changes something about that, and this is called conditional convergence. So absolute convergence, back up here to this theorem here, is when you take the absolute value and the absolute value of this series converges, you're guaranteed that the non-absolute value part converges. And so something is absolute convergent when both converge, and conditionally convergent when only one of them converges. So when the absolute value diverges and the regular series converges. So I'm actually going to take you down here to a little flowchart on the next page if you want to flip it over. And these are two strategies that you can take when trying to determine absolute convergence. So flowchart 1, the strategy is to first test the regular version, and you decide if it converges or diverges. And if it diverges, then that guy just diverges. And then if you go to, then the next step is to test the absolute value version. And if the absolute value converges, then it absolutely converges. And if the absolute value diverges, then we're looking at conditional convergence because the regular one converges. I tend to follow flowchart 2 here, so this will be the way that I do it. And this one, instead of testing the regular series first, you test the absolute value first. And if you get convergent, then you're done because of the theorem that we had at the beginning. And we know that the original series is absolutely convergent. And then if you get diverges, then you go and you test the original series to see if it is convergent or divergent. And then that if they're divergent, then we just diverge. And if it's if it converges, we're conditionally convergent. So you can follow either one, but I will primarily follow flowchart 2. So let's go see an example of this now. So, personally, I start by testing the absolute value of the series first. following flowchart 2. So we will take the absolute value, and that's going to make the -1 to the n go away, and so we'll just be looking at n equals 0 to infinity of n factorial over 2 to the n. So we need to run some sort of test on this. And this looks like something where we're going to run we can always think about the nth term test for divergence first. So if we think about the limit as n approaches infinity here, the top will grow faster than the bottom, and so this will go to infinity. So because the factorials always grow the fastest. So this is actually a good nth term test for divergence. So if we do the limit as n approaches infinity of n factorial over 2 to the n, this is going to be infinity because the top grows faster than the bottom. And so this is not 0. So if we are calling this original series here a sub n, okay, we just tested here the absolute value of that. So we took away the alternating part and we were just testing the absolute value. And this guy diverges by the nth term test. And now the other situation is the original series itself with the alternating part. This guy could converge or diverge. If this converges, then we converge conditionally because we have diverges and we'll have converges. If this diverges, then we just have divergence, period, no matter whether it's the alternating or the absolute value. So now we're going to test the original series itself. So up here we tested the absolute value. Down here we're going to test the original series. So we're going to leave the alternating part. So usually this is going to be in the alternating series test because it'll usually be an alternating part. And so we'll do the limit as n approaches infinity of n factorial over 2 to the n. We already know that's infinity, which is not 0 because we already talked about this. So this one also diverges. Or what we were calling just the original series, an, this diverges by the nth term test. So in this case, we would just say that both diverge. So we would just say that the original series diverges. Because both the absolute value diverge and the series itself diverges. So this is our conclusion here. So you might think, well, wouldn't that always happen? Well, let's look at some examples here. And we'll see a case where this doesn't happen. So first up here, remember, this is our series. We're going to call this n equals 1 to infinity of -1 to the n over square root of n. This is going to be a sub n, right? So first we'll take the absolute value and we'll test that first. Again, you can do it in the opposite order. It's all personal preference. So the absolute value of our series here is going to just be 1 over the square root of n. Now this is a p series with p equal to 1/2. And so by the p series test, this guy diverges because this is less than 1. So the absolute value diverges, this one, the absolute value. So that happened over here too. The absolute value diverged. Okay, and so now we're going to go and we're going to test the original series, just an. So we'll look at this series. This is an alternating series. When we don't get rid of the alternating part, well, usually you're going to use the alternating series test on this. So we'll do the limit as n approaches infinity of 1 over the square root of n, and that's going to be 0. And then we want to see if an plus 1 is less than this, which adding 1 to the bottom there will make it smaller. So this is a decreasing series whose limits goes to 0. So the original series converges by the alternating series test. So this is different. Over here, right, the original series diverged and the absolute value diverged. So that just diverged. But now the absolute value version diverged and the original series, the alternating series, converges. So this is exactly what we call conditional convergence. So we would say our original series here converges conditionally. Because the absolute value version without the alternating part diverges, but then you put the alternating part back in and this converges. And that's exactly what conditional convergence is. So now let's do a couple more examples. All right, a couple more examples here to get the hang of this. I'll go ahead and leave the flow chart up here. Again, if you'd rather start by testing the original, you can do this, and then if you get diverge, you're just done. You say diverges. If you get converges, you have to test the absolute value. It's just the opposite of what I'm doing. I'm starting with testing the absolute value. If I get diverges, we'll see if it's conditional. And we're going to run into an example here where it goes this way now. So we'll start by testing the absolute value. And that will make the -1 part go away. Everything else will be positive. And this guy almost looks like a p-series, but we need to simplify these two to see truly what p-series it will behave like. So if we look at n equals 1 to infinity, and we look at what square root of n over n squared simplifies to, this will simplify down to 1 over n to the 3/2. So here we will compare to one over n to the 3/2. This guy is a p-series with p equal to 3/2, which is less than 1. So this converges. So we would expect that this guy also converges, but we need to show that using one of our comparison tests. This will probably be a pretty easy direct comparison test. If you want to compare, remember this guy right here is the same thing as that. So if we want to compare square root of n over n squared plus 1, and just the square root of n over n squared, then here the only difference is that we are adding 1 to the denominator over here. So this one will be smaller. And so we know something about this series. This is a convergent, and this is the bigger series converging. So then that tells us that the smaller series will converge. So then we can say this converges by direct comparison test. And when I say converges, I'm talking about the absolute value, right, without the negative, converges by the direct comparison test. Now, this flowchart is where we get to stop. When we get over here to converging, if the absolute value converges, that theorem from the very first page said that the original series is going to converge. So we don't even have to test the original series. If you get that the absolute value converges, you know the original series converges. That's what that theorem at the beginning helped us with. So we don't even have to test it. If you did, you could run the alternating series test on this and you will get converges. But we don't need to because of the theorem. It says if the absolute value converges, then the original series converges. And so we will say that the original series converges absolutely. Sorry, no absolute value here. The original series converges absolutely. Because both converge. The absolute value converges, and because of our theorem, we already know that the non-absolute value converges. Now you could, again, take the alternating series test and write it on that and you'll get convergence, but you don't have to because of that theorem. So this is what converges absolutely looks like when they both converge. So we either conditional converge when one converges and the other diverges, or you both diverge and diverge, or both converge and converge absolutely, right? So those are your three options. So let's do one more example. So we'll start by testing the absolute value. And so that will make the -1 to the n go away. Everything else will be positive, so it will just be 2k over k squared. And if I look at this, I can already see that the top is growing faster than the bottom because 2 to the k is bigger than k squared. So I can already tell right away that the limit as n approaches infinity of 2 to the k over k squared. 2 to the k is an exponential. It's going to grow faster than k squared, so this limit will be infinity, which is not 0. So this guy, the absolute value, diverges by the nth term test. And so then we need to look at the original series itself. With the alternating part and test it. And since it's alternating, the first thing we'll do is do the limit as k approaches infinity of 1 over k squared, 2 to the k over 1 over k squared, the part without the alternating. And that limit is going to be infinity. We already did that a second ago, which is not 0. So this guy also diverges by the nth term test. So in general, we will say that this guy diverges because both diverge. The absolute value and the non-absolute value both diverge. So this guy just diverges. So both diverging means divergence. One diverging, one converging means convergence. And what you might have noticed in this example and from one of the other ones earlier, if you get that the absolute value diverges by the nth term test, then the original series is also going to diverge by the nth term test. But if you look back at our example that we did earlier, over here, B, this one, when we concluded that the first series, the absolute value, diverged, it was because of, so this first example here diverged because of the P series test, not because of the nth term test. And that's why we ended up with conditional convergence, because then the non-absolute value with the alternating converged by the alternating series test. And again, if you would rather follow flowchart 1, you're going to run into the same situation. If you test the original and you get that it diverges, then they're both going to diverge, right? So you would just get diverges. So the only difference between both flowcharts is which one you're testing first, the absolute value or the non-absolute value. So if one of them makes more sense than the other, then just pick that strategy. It's really just two different strategies. But overall, you basically need to test the absolute value and the non-absolute value. When it's the non-absolute value, usually use the alternating series test. Otherwise, you're going to have to use another test. If both converge, we get absolutely converge. One converges, one diverges. We have conditional convergence. And if they both diverge, then we just diverge. that is all.